Today we are going to talk about operational amplifiers. And we are going to take a look specifically at the ideal op-amp. So the operational amplifier, or op-amp, are integrated circuit devices. Used to perform mathematical operations on signals. So anybody here, let's start with something easy. Anybody here know what an integrated circuit is? Anybody at all? Okay. So an integrated circuit is just a circuit that is monolithically integrated onto a single chip. So monolithically literally means it's all on one substrate or all in one package. So I'm going to open up a file here, which is actually a simplified look at a MUA 741 op-amp. Okay, so this is a very general purpose op-amp. And this is what the schematic diagram for that op-amp looks like. Okay. So this particular guy uses, let's scroll down here, 22 bipolar junction transistors, 11 resistors, a diode, and a capacitor to perform its operation. Now, in this class, transistors and diodes mean absolutely nothing to us because they are nonlinear circuit elements. It's not actually until you get into your junior electrical engineering classes until those components are introduced in any real way, shape, or form. Okay? But as complicated as this thing looks, and it is very complicated, it actually behaves in a very, very simple way in performing mathematical operations on signals. Okay? So the schematic representation of that op-amp, instead of being that terrifyingly huge circuit, is just this. We have a triangle, which is the generic representation of any amplifier. Our op-amp is a differential amplifier, meaning it has two inputs. Okay. So one input we're going to designate with a plus sign. The other input we're going to designate with a minus sign. All right. The input on the plus sign is what's called the non-inverting input. And the one on the minus sign is what's called the inverting input. On the opposite side here, we have the output terminal. So let's talk a little bit about what the non-inverting input terminal and the inverting input terminal does. Okay. The operational amplifier at its heart is a voltage amplifier, which means it takes voltage signals at its input, operates on them in some way, and then generates a voltage signal at its output, okay? If you were to apply a voltage signal at the non-inverting input with the inverting input grounded, whatever polarity that signal has gets carried to the output. So if you put a positive voltage on the non-inverting input pin, you should expect a positive voltage at the output pin. The inverting input is used to invert the polarity of signals. So if you put a positive voltage on the inverting input pin, you should expect to see a negative voltage on the output pin. That's it. That's what the non-inverting and inverting means. Non-inverting keeps the polarity, inverting changes the polarity. Okay. Now, if we look here, we've taken care of in plus and in minus and out. We have two terminals called offset N1 and offset N2. Those two terminals are used to correct manufacturing errors in the device, okay? So all that really means is you could take this device and you could actually short out the two inputs and see some small output signal due to the way that these devices are constructed. Those two pins are used to bring that offset down to 0 so that no input gives you no output. Those two pins mean absolutely nothing to us in this class whatsoever. So we're not even going to bother to draw, okay? Then we have up here at the very top right, a pin that says VCC plus, and at the very bottom right, a pin that says VCC minus. These are where we apply power supply voltages, okay? So this is an active device. What that means is it doesn't work or it doesn't do its job unless it's powered, okay? So a resistor exhibits resistance regardless of whether or not it's in a circuit. A capacitor exhibits capacitance whether or not it's actually in a circuit. And an inductor exhibits inductance whether or not it's in a circuit. An operational amplifier does not behave as an amplifier unless you power it, okay? So it doesn't do anything unless you plug it in and give it some sort of power. So we're going to represent those power supply terminals here. And I'm going to do them in pink because for the sake of our class, they're largely optional. Okay. So I'm going to call this guy VCC plus and VCC minus. Okay. So this is where we would apply a positive power supply voltage and a negative power supply voltage. Now, when I say for this class, they're effectively optional, in our analysis, they won't show up literally at all. When we do a lab using these components on Friday, if you don't remember to connect the power to these terminals, your circuit won't behave correctly, okay? So for our analysis, we're not going to see these guys again, but for our practical use of op amps, they're very, very important. What the power supply terminals do in a practical or physical op amp circuit is they provide power to the device, and they also set an absolute reference value for the circuit as well. So the output voltage can never be higher than the positive power supply voltage, and it can never be lower or more negative than the negative supply voltage. It'll actually cut those signals off, and we can play around with the power supplies and the gain of our system on Friday and actually observe that happening if we choose to do so. Okay? But for the purpose of our analysis in this class, we're largely going to focus on these three terminals that I've laid out here in black: our non-inverting input terminal, our inverting input terminal, and our output terminal. And we are going to work to develop relationships between input signals and output signals. Okay? Now in this class, we are focusing on the ideal operational amplifier, okay? The ideal operational amplifier is actually governed by exactly two rules, okay? The first rule, let me do these not in pink. Ideal OpAmp rules. And apparently I can't spell rules today. So the first rule is that no current can flow into or out of the input terminals. So if I call this current I superscript minus, hold on just a second, that's going to be wildly annoying, so let me save this and reopen it. Engineering 12 sheets, there we go. All right, that was just going to be annoying and loud the next 10 minutes. I didn't do that. So I'm going to call this current I superscript minus, and that is the current flowing into the inverting input terminal. It is always 0 if we are analyzing a circuit that uses an ideal OpAmp, which is all we're going to talk about in circuits 1. Similarly, I can call this current up here I plus, and it has to be 0 as well. Okay. So both of these currents are always 0 amps. Okay. This is because the internal input resistance of an operational amplifier is usually on the order of a few mega ohms, so 10 to the 6 ohms, all the way up to a few tera ohms, or 10 to the 12 ohms. So the resistance that we would see looking in, the Thevenin equivalent resistance that we would see looking into this device through those two input terminals is enormous compared to most resistors we would ever actually use in an OpAmp circuit. So no current flows into or out of the input terminals. Our second rule is there is no voltage difference between the input terminals. So if I call the voltage here V plus, so this is just representing the voltage at the non-inverting input terminal with respect to ground. For OpAmp circuits, we're going to be dealing with nodal voltages the entire time. So a V plus is the voltage present at the non-inverting input terminal with respect to ground. This guy down here, V minus, is the voltage present at the inverting input terminal with respect to ground. Rule 2 tells us that V plus has to be exactly the same quantity as V minus. This constraint occurs because the open loop gain of the OpAmp is extremely high, on the order of a few 100,000 usually. Okay? Now we are going to be using these in what's called a closed loop configuration, and I'll explain what that means in a moment when we analyze a circuit. Okay? So these are our two rules. We are going to take these two rules and then apply simple circuit analysis techniques like KCL, KVL, and Ohm's law, and be able to develop a means by which to analyze really any OpAmp circuit we could think about. Okay. So Let's start with our first example. We're going to have an op-amp circuit. Like so. In this instance, I'm drawing my inverting input terminal on top, my non-inverting input terminal on bottom. It does not matter if I flip those back and forth as long as they're behaving the way they're supposed to. Okay. I'm going to apply a voltage of 3 volts here. And then I'm going to apply what's called a feedback resistor. Here, and let's make this guy 4 kilo ohms. Typically speaking, you'll see op-amp circuits are biased by kilo ohm size resistors for a very specific reason that is not remotely important to what's going on in this class. And let's put a resistor here. Let's call it 5 kilo ohms, like so. And then our output voltage, so this is literally the voltage measured at the output pin. Will be the voltage drop also over our 5 kilo ohm resistor. Okay. We want to analyze this circuit. So what we are going to do first is apply OpAmp rule 1, which says this current is 0 amps, and this current is 0 amps. And we're going to try to identify this voltage V plus, and therefore this voltage V minus. All right. So can anybody tell me what the voltage V plus is? The voltage present at the non-inverting input terminal of our op-amp. It's not a trick question. 3 volts. We can literally see it. Okay, not a trick question at all. So we have 3 volts as V plus. So according to op-amp rule, what's V minus? Also 3 volts. We don't need to do any analysis. That sentiment has to be true. Okay. So let me ask you guys a slightly different question. What's that voltage VR there? The voltage drop across my 4 kilo ohm resistor. 0. Why, Carter? Exactly correct. No current can flow through that 4 kilo ohm resistor because that 4 kilo ohm resistor is connected directly to my input terminal. Okay. So if VR is 0, what's V out? 3 volts. Okay. So effectively, let me do this in orange. That seems good. I can do Kirchhoff's voltage law around this path, where I'm starting at ground and I'm ending at ground. So it's a complete loop. And I can see that -3 volts plus VR, which we know to be 0 volts, plus V out is equal to 0, which tells me that V out is 3 volts. Have we introduced any new or fancy analysis techniques here? Not at all, right? For these OpAmp circuits, we are just going to go back to fundamentals the overwhelming majority of the time. Okay. Anybody have any questions about the analysis that we've done here? Anything seem particularly difficult or confusing? All right. Let's take a crack at another one. Plus, minus. So this time, let's short out our non-inverting input terminal. Let's throw a 2 kilo ohm resistor here. Let's throw a 4 kilo ohm resistor here. This is going to be V out, which is the voltage drop across the 4 kilo ohm resistor, since V out represents a nodal voltage. And let's put a 3 milliamp current source. At this terminal. So what we're going to do again, we're going to apply OpAmp rule 1, be very explicit about the fact that there's no current flowing here or here. So Dylan, what's V plus? 0. So Kai, what's V minus? Also 0. Okay, so both of those voltages are 0. So what's the voltage drop over my resistor VR here? Either of my Jacobs. It will not be. Okay. So let's talk about this. We have that 3 milliamp current source on the left-hand side of the circuit, right? So I'm going to draw in purple here that current's path. So it can flow up here, and then it reaches this point. And we know for sure that none of it can branch off and flow into the input terminal, which means all of it is going to flow into our 2 kilo ohm resistor. So if we know that there's 3 milliamps of current flowing into our 2 kilo ohm resistor, what's the voltage drop over it? 6 volts. Absolutely right. So from this, what's V out? I disagree. If we do KVL, around this path, right, what we see is 0 volts plus 6 volts, the voltage drop across our resistor, plus V out is equal to 0, which means V out is equal to negative 6 volts. So what did I tell you guys about what the inverting input does? It changes the sign. So we have a positive input signal being applied to the inverting input terminal. We should expect to see a negative output. All right? Does that make sense? That's literally what the purpose of the inverting input signal is. Okay. Let's mess this up by introducing 2 inputs. Sorry, this should be 3. Like so. Okay, so let's say that we have a 3-volt source. Let's do that same 2 kilo ohm resistor up here. That same 4 kilo ohm resistor here. And that same 3 milliamp source here. You should be able to tell me what the output voltage of this system is literally by looking at it based on the results of our last 2 problems. It's okay if you don't see that. We can apply our rules and follow through our analysis just like we've been doing, and we'll wind up getting the same result. Right? So let's do it using the rules. We should get in the practice of doing that. Okay. Our current here is obviously 0 amps. Our current here is obviously 0 amps. Our voltage here is V plus. Our voltage here is V minus. What, McKinley, what's V plus? Abigail, what's V minus? 3 volts, absolutely right, okay? What's the voltage drop across this resistor? VR, Brittany. 6 volts. Right? So all 3 milliamps of current flows through that 2 kilo ohm resistor again. So Sully, take a crack at V out. Negative 3 volts. Yeah. So we could find that by saying negative 3 volts plus 6 volts plus V out is equal to 0. Therefore, V out must equal to negative 3 volts. Or we could have analyzed this guy using superposition and find out that it's just a combination of the last 2 circuits that we analyzed. Literally. With the voltage source on and the current source off, it's example 1. With the current source on and the voltage source off, It's example 2. Add those results together. Things like superposition absolutely still work. Bradley. That's a fantastic question. Let's work that problem. Okay. So what was asked is what happens if we put a voltage source on that leg of the resistor? Wonderful question. So let's put a 2-volt source here. Let's put a 4 kilo ohm resistor here. And then I am going to cheat a little bit. Okay. Let's put a 10 kilo ohm resistor here. Let's call this V out. And I'm going to put a resistor here that is 1 kilo ohm, and then throw a voltage source over here. Let's call this guy 4 volts. So this resistor, Bradley, is ensuring. So rule number 2 says that there can't be a potential difference between the inverting input terminal and the non-inverting input terminal. That 1 kilo ohm resistor right there is going to allow that to happen even though I have another voltage source. If I didn't have that 1 kilo ohm resistor there, I couldn't use ideal op-amp rules because there obviously is a potential difference between the two. Okay, so that 1 kilo ohm resistor fixes that problem. All right. So let's take a stab at analyzing this circuit. Okay. Well, actually, before we do that, have we noticed anything interesting about these 3 examples? Anybody? Has our output or load resistor here, so the 5 kilo ohm resistor in the first example, the 4 kilo ohm resistor in the second and third example, has that even been used in any of our equations? Not at all. For an ideal op-amp circuit, the resistance that we load it with is unimportant. As long as it's not a short circuit, which forces output to be 0, right? If we directly short the output terminal to ground, it can't have any other value than 0. But if we have any finite or actually any non-zero resistor value, V out doesn't care what that resistor is. Okay, so we can start drawing it as an open circuit voltage at the output and get the exact same results. All right. Let's slightly modify our methodology here. Okay. So what we've been doing is we've been determining V plus and then determining V minus and then doing KVL around a loop to find out what the output voltage is. There's nothing remotely wrong with that whatsoever, but we'll find that when we have multiple voltage inputs, it might be easier to, instead of doing KVL, to use KCL at the inverting input terminal specifically. Okay. So let me explain what I mean by that. We know that this current is 0. We know that this current is 0. Skylar, what's V plus? All right, I'm going to write that down. Haley, I believe, what's V minus? Also 2 volts, absolutely right. So instead of doing KVL around this guy and figuring out what that voltage drop is, let's approach it in a slightly different way and say, let's apply KCL at the inverting input node. Okay. If we apply KCL right here, what we'll find is that V minus 4 volts over 1 kilo ohm is equal to V minus V out over 4 kilo ohms. And since V plus is equal to V out, we have a one equation, one unknown system that we can solve for V out very easily. This methodology, finding the voltage at, applying op-amp rule number 1, and then finding the voltage at the non-inverting input terminal, and then applying KCL at the inverting input terminal, will allow us to calculate V out for practically every op-amp circuit we're going to deal with in this class, regardless of its complexity. Okay. So this guy, I would argue, is a little bit more complex than what we've been dealing with. But this simple methodology would allow us to solve for V out, and we would find, let's see, get a calculator here. Can't quite do this one in my head. Numerical solver. So we're going to have x minus 4 over 1,000. No, actually, that's not x minus 4 because we know that one. Sorry. 2 minus 4 over 1,000 is equal to 2 minus x over 4,000. And if we solve that, we find that our output voltage, V out, is equal to 10 volts. We would get the exact same result if we solve the problem the other way, but we would struggle to figure out how much current is flowing through that 4 kilo ohm resistor to find the voltage drop over that guy. Whereas if we do it this way, that current is kind of buried into our analysis. Okay. Let's do something. I'm going to draw probably the hardest question I could give you guys on an exam dealing with op amps. If you look at my old test, you'll probably see something very similar to this. Okay. Let's make this guy a 3 kilo ohm. Let's make this guy a 6 kilo ohm. And then let's put a voltage source here. That is 2 volts. And 10 kilo ohm resistor here. Okay. We're going to do the exact same steps we did in the last problem, which was significantly less complicated than this one. Okay. So Carol, what's the current flowing? Oh, I just wrote it down actually. So if we know that these currents are 0 amps, what is the voltage V plus? Neither. Okay, so let's talk about that. All right. So our rule says that no current can flow into the input terminal, right? So where does this 2 milliamps of current go? Through the 3 kilo ohm resistor, exactly right. So it just flows down here, okay? Since there's no voltage drop over the 1 kilo ohm resistor, because we know for a fact that no current can flow through it, the voltage at this node is also V plus, right? If there's no voltage drop over that 1 kilo ohm resistor, we can effectively treat it as if it were a short circuit. So I'm gonna let you take another crack at that voltage since you know exactly how much current flows through that 3 kilo ohm resistor. 6 volts, right? So V plus is equal to 6 volts. We got that just using Ohm's law, nothing remotely fancy or anything, right? Okay. Simply by recognizing none of that 2 milliamps of current can branch off and flow into the input terminal. So all of it has to flow down through the 3 kilo ohm resistor. Okay. So now what we're going to do is we're going to apply Kirchhoff's current law at the inverting input terminal, which means we're going to add this current, and this current together and solve for V out. Kennedy, could you help me with this equation? All right. All right. Wonderfully done. You effectively, once you throw that equation into a calculator, have solved literally one of the hardest problems I could possibly give you on this topic. And we're only 35, 40 minutes into the lecture. Being able to write that equation effectively exhibits the better part of mastery for these type of problems with respect to circuit form. Okay. I can't give you anything more difficult than that. So let's solve this guy for V out. We all have our calculators. Tell me what you get. Pardon? 10.2. All righty. Do we need to keep working example problems? This is literally as hard as it gets. Is this one for? Yeah. Sure. Absolutely. So that's a fantastic question. Okay. So if the output voltage is non-zero, then there is a voltage drop of V out over the 10 kilo ohm resistor, which means there's current flowing through the 10 kilo ohm resistor. Now, here's a, let's look at example 1 here. Okay, just real quick as something. If that 5 kilo ohm resistor were an open circuit, actually, let's not do that one. Let's do the next one because it'll be more obvious. Sorry. If this 4 kilo ohm resistor were an open circuit, we are following that current in purple from the source through the 2 kilo ohm resistor. Where does it go? If that's an open circuit, how can it go straight down? It's going to go into the output terminal, right? So OpAmp rule number 1 says that current cannot flow into or out of the input terminals of the OpAmp. It does not say anything about current flowing into or out of the output terminal. So effectively, if we had open circuited one of these guys, we can't really see the effects of where the current is going into or where the current is going because we're not including the power supply terminals or the internal circuitry or anything like that. But the path to ground is actually back into the OpAmp, into the output terminal, and then to ground through the power supply. But that's not remotely necessary to understand in order to analyze these circuits. That's a very good question. Yeah. So OpAmp rule number 1 is only regarding the input terminals of the OpAmp. Current can absolutely flow into or out of the output terminal as is needed. All right, so I ask you guys again, we want to keep working problems, or do you guys want to take a crack at your in-class assignments or even your homework set? Truthfully, your homework set for this first bit, I don't want to discourage anybody, but I feel like if you can't knock it out in half an hour or less, you probably need to ask a couple of questions to clarify a few things. It's like 6 problems, but it's fairly, if you apply those 2 rules, you should be pretty good to go. All right.